Hello students, this is Mr. Deaver here. Well, last week we learned some basic things about solutions and dissolving, and this week we're going to go more in depth about dissolving and dissociating, and we want to see what is the difference between dissolve and dissociate, what kinds of substances dissolve and why, and what kinds of substances dissociate and why. So last week we learned a bunch of vocabulary words. It might be helpful to review those. We're going to look at two pictures here, and we want to see if we can describe what's happening in these pictures using some of these vocabulary words. So, both of these, are they solutions? Yes, they're both solutions. Right here in salt water, which is the solute? Salt is the solute, and water is the solvent. Remember that the solute is what gets dissolved, and the solute gets dissolved in the solvent. So, solute gets dissolved in the solvent, salt gets dissolved in water. Here, sugar is the solute, and water is the solvent. Okay, so these are both solutions. They're both showing us some dissolving. But let's see if we can go again, look at the definitions and see which pictures are showing dissolving and which are showing dissociating. Well, what does it mean to dissolve? Dissolve is when the solute separates from itself and interacts with the solvent. So are there interactions between the solute and the solvent? So here's our salt particles. Here's our water particles. Are they interacting? Yes, they're interacting, so they are dissolving. Excellent. What about dissociation? Dissociation is when a substance splits into smaller particles. Is the salt splitting into smaller particles? Yep, it is. So it's both interacting with the water, it's dissolving, and this salt is actually breaking apart into individual atoms. The salt is both dissolving and dissociating. Okay, here we have some sugar molecules. So is the sugar dissolving in water? Is it interacting with the water? Well, yes, we can see here that the water is surrounding the sugar molecules. They are interacting, so they are dissolving. Is it dissociating? Is it breaking apart and splitting apart into smaller particles? No, this sugar molecule is staying one single big sugar molecule, right? These are all separate sugar molecules. They are separate, but they didn't break apart into single atoms like the salt did. So this is dissolving, but not dissociating. It's only dissolving. So again, we want to start to understand why. Why do some things dissolve? Why do some things not dissolve? Why do some things dissociate? Why do they break apart like this? And why do some things not dissociate? Well, to understand that, we have got to review a couple things about nonpolar, polar, and also ionic. So we've learned these pretty recently, but they're really important to understand dissolving and dissociating. So a quick review is that nonpolar bonds are when electrons are shared, but they're shared equally. So both chlorines want electrons the same amount, and therefore the electrons do not get pulled to one side or the other. So there's no positive and negative side on a nonpolar bond. That's really important. There's no positive and no negative. However, in a polar bond, this chlorine is more electronegative than hydrogen. That's a word that we've learned before. That chlorine wants electrons more, so it pulls the electrons to this side. The electrons get pulled to one side. That's why we drew the arrows on the molecules before, to show where the electrons are getting pulled. And so therefore, there's a negative side and a positive side. All right, now this is on your note sheet. So you should have a note sheet, and I want you to write this down on your note sheet. We're going to review ionic, polar, and nonpolar and write down some things. Now, ionic, we have learned before, but it has been a little while. So ionic, we need our periodic table to help us figure out if something is ionic or not. Do you see this dark line here, this staircase? Do you remember what this means? Okay, this staircase separates the metals over here, all these on the left side. These are our metals. These are positive. These on the right side, these are non-metals. These are negative. However, there is one element on the left side that is special. That's a non-metal. Do you know which one that is? Hydrogen. Hydrogen, even though it's on the left side, it's a non-metal. It's really more similar to these over here. So again, left side, metal, except for hydrogen. Right side, non-metal. So when we have a negative metal and a positive metal and a negative non-metal, we know what happens to positive and negatives. They attract. And that's what makes an ionic bond. An ionic bond, an ionic compound, has a positive metal from the left side of the periodic table and a negative nonmetal from the right side of the periodic table. Okay, so an example of something that's ionic is sodium chloride. Sodium is right here. It's on the left side. It's a metal. Chlorine's right here. It's on the right side. It's a nonmetal. So sodium chloride, or salt, is an example of an ionic compound. Polar, something we just talked about. Remember that? Now, to really tell if something is polar or not, we have to draw the arrows on it. But this will work 90% of the time. Okay? Polar molecules are made of only nonmetals. Remember, these nonmetals are over here. On the right side, these are nonmetals, and then also hydrogen is a nonmetal. So it's made of only nonmetals, but it's made of different nonmetals. So an example of that is H2O. Okay, O is on the right side. It's a nonmetal. Hydrogen, even though it's on the left side, it's an exception. It's a nonmetal. So we have different nonmetals. Water is polar. And we also know that polar things have a negative side and a positive side, and that's really important. In fact, both ionic and polar substances have positive and negative. That's really important. Okay, what about nonpolar things? Are they made of metals or nonmetals? Well, nonpolar things are also made of only nonmetals. However, they're made of all the same nonmetals. For example, Cl2. It has the exact same nonmetal, right? Cl and Cl. Or it has only C and H. C and H make a nonpolar bond, okay? Now, remember that nonpolar bonds have electrons that are shared equally. There's no positive and negative side here. So nonpolar molecules do not have a positive and negative side. And chlorine, Cl2, is an example of a nonpolar molecule. So you need to be able to use these rules to figure out if something is ionic, polar, or nonpolar, because that tells us if it will dissolve or dissociate. So if you need to review this, please spend some time to review that. Okay, now, why do things dissolve or dissociate? It really has a lot to do with positive and negative. So we just said that water, H2O, is polar. It has a positive and negative. So here we have water molecules and we have sodium chloride, salt. Look what happens to the negative side of the water and the positive sodium. They attract. Same thing with the negative chloride and the positive hydrogen. They attract. So when we have positive and negatives, it dissolves in the water because the positive and negatives attract. This is this idea that like dissolves like. Things that are positive and negative, like water, will dissolve in water because those positives and negatives attract. Same thing with alcohol. Alcohol is actually really similar to, well, never mind. Okay, alcohol has a negative and a positive side because that OH bond is polar. Hey, guess what? Water also has a positive and negative side because it's polar. What happens to that negative and positive? They attract. Therefore, polar things dissolve in polar things because like dissolves like. Negatives and positive interact, and they can dissolve in each other. What about oil here? Oil has only carbon and hydrogen. Now, what did we just say about carbon and hydrogen? If something has only carbon and hydrogen, it's nonpolar. It does not have a positive and negative side. Water does, though. Water has positive and negative sides, but oil does not. So there's no attraction here between water and oil. And do they dissolve? No. Look at how separate they are. The oil goes on top of the water. And now you know why. It's because oil is nonpolar. It doesn't have positive and negative. And water is polar. It does have positive and negative. And they don't attract. So they don't dissolve. So let's summarize this on this table, which again is in your notes. So sodium chloride, we've already said. Sodium, left side, positive metal. Chlorine, right side, negative nonmetal. This is an ionic compound. Ionic compounds have positive and negative, just like water. So ionic substances do dissolve. In addition, ionic substances dissociate. They split apart into individual atoms, like we see in the picture here. Sugar. Now, sugar has carbon, hydrogen, and oxygen. Here's carbon, it's the right side, it's a nonmetal. Here's oxygen, it's the right side, it's a nonmetal. Hydrogen is also a nonmetal, even though it's on this side, it's an exception. So this is made of different nonmetals, right? They're not all the same. We have 3 different elements, so we have different nonmetals. It's polar. Polar things have positive and negative sides, therefore they dissolve. They interact with the water. But is the sugar breaking apart into individual atoms? No, it's not dissociating. Only ionic things dissociate. Ionic things dissolve and dissociate in water. Polar substances dissolve but do not dissociate in water. Okay, what about oil here? Well, we can see what's happening. This is the formula for oil. It's only carbon and only hydrogen. We know that things that are only carbon and only hydrogen are nonpolar. So, nonpolar things, they do not have a positive and negative side. So it's nonpolar. Does it dissolve? No, because it doesn't have a positive and negative side. And it also doesn't dissociate because only ionic things dissociate. So this is a really important table. This summarizes what you really have to know from this video. Let's practice a bit with 3 examples here, okay? The first substance is F2. Is it ionic, polar, or nonpolar? Well, F, fluorine, is over here on the right side. Is it a metal or a nonmetal? It's a nonmetal. And this substance does it have different nonmetals or all the same nonmetal? All the same nonmetal, right? It has only fluorine atoms, so it's nonpolar. We have all the same nonmetals, it's nonpolar. Do nonpolar things dissolve in water? Remember, nonpolar? No, it does not dissolve. Okay? And it does not dissociate. All right? I'm actually going to do this one last. We're going to leave that for last, okay? Let's think about CH3OH. This is methanol. Okay? Here we have carbon, it's a nonmetal. Oxygen, it's a nonmetal. Hydrogen, even though it's on the left side, it's a nonmetal. Everything else on this left side is a metal. Copper, zinc, titanium, calcium, sodium, cesium, all metals on this left side, except for hydrogen. It's a nonmetal. So these are all nonmetals, but they're all different nonmetals. This is polar. If we were to draw arrows on this, we'd see the arrows pointing towards the O, because the O is really negative. It's really electronegative, and it pulls electrons toward it. So this is going to have a positive and negative side. It's going to dissolve, because polar things dissolve, but it's not going to dissociate, right? Just like our table, polar, yes, it dissolves. No, it does not dissociate. Okay, what about magnesium chloride, MgCl2? Here's magnesium. It's on the left side. It's a positive metal. Here's chloride. It's on the right side. It's a negative nonmetal. We have a metal and nonmetal. Therefore, it is ionic. Okay, according to our notes, do ionic things dissolve in water? Yes, they do. Do ionic things dissociate in water? Yes, they do, right? This is from our summary table here. Ionic things both dissolve and dissociate. Now, let's go back and do this last step, the number of particles. Remember that when things dissociate, they are going to split apart into individual atoms. Look at here how the sodium and chloride split apart into individual atoms. So let's imagine that this substance is ionic, it dissociates, it's going to split or break apart into individual atoms. How many particles will there be after it dissociates? Well, let's look at the formula. How many magnesium atoms are there? Just one, right? There's no number here, so there's just one magnesium atom. How many chlorine atoms are there here? Two. So one magnesium atom plus two chlorine atoms equals 3. There's going to be 3 particles because this is going to dissociate or split apart into 3 particles. But it only splits apart if it dissociates. This does not dissociate. Is it going to split apart into different atoms? No. So then this one particle will stay together. If one particle stays together and doesn't break apart, then we still have one particle afterwards. What about this? Does this substance dissociate or split apart? No, it doesn't. So we had one whole particle before, and we have one whole particle after. So basically, if something does not dissociate, then you're always going to have a 1 here, because this stays together. This stays together. It's one particle here. After, it's still one particle. But if something dissociates and splits apart into individual atoms, then you have to look in here and count. 1 magnesium plus 2 chlorine equals 3 particles after. So those are some examples. There's some more practice for you online. Good luck.